Look up at the night sky. Every star you see is a memory. The light from Sirius left 8 years ago. From Betelgeuse, 600. From the Andromeda Galaxy, 2.5 million years ago, when our ancestors were learning to walk upright. We are time travelers, looking into the past. But what about the future? What about traveling to those stars within a human lifetime? For over a century, physics has answered with a resounding, mathematical no. Nothing can travel faster than light. It is not a suggestion, not a technological hurdle. It is woven into the fundamental geometry of reality itself. But recently, a strange loophole appeared in the mathematics. Not a way to break the law, but a way to sidestep it. A theoretical concept that suggests faster-than-light travel might be mathematically possible, even if physically unimaginable. What scientists found, however, was not a door to the stars, but a revelation about the universe itself. The speed of light is not just a limit, it is a guardian. And it is defended by layers of constraints, each more profound than the last. This is the story of why we cannot outrun light, and what that impossibility teaches us about the cosmos we call home. To understand why light speed is a universal constant, we must first dismantle our intuition about motion. In our everyday experience, speeds add. If you walk forward on a moving train, your speed relative to the ground is your walking speed plus the train's speed. This is Newton's world, and it works perfectly for everything from cars to cannonballs. But in the late 19th century, Scottish physicist James Clerk Maxwell derived a set of equations describing electricity, magnetism, and light. And buried in those equations was a number, approximately 300,000 kilometers per second, the speed of light. Strangely, this speed appeared as a constant, with no reference to the motion of the source or observer. This troubled physicists. If light was a wave, like sound, it should travel relative to some medium, a luminiferous ether. And if you move through that ether, you should measure light moving faster or slower, just as you hear a train horn change pitch as it passes. But experiment after experiment, most famously the Michelson-Morley experiment in 1887, found no evidence of this ether. No matter how Earth moved through space, the speed of light remained stubbornly, inexplicably constant. It was as if the universe had a preferred speed limit, and every observer, regardless of their motion, agreed on it. In 1905, a young patent clerk named Albert Einstein proposed a radical solution. What if, he asked, the speed of light is constant for all observers? What if, instead of light adapting to our motion, space and time themselves adjust to keep light's speed unchanged? This was the birth of special relativity, and its consequences were nothing short of revolutionary. Einstein showed that if the speed of light is constant, then time cannot be absolute. A clock in motion ticks slower than one at rest. Distances contract in the direction of motion. Events that are simultaneous for one observer may occur at different times for another. These are not optical illusions. They are properties of spacetime itself. As an object accelerates toward the speed of light, its relativistic mass increases. Not because it gains physical matter, but because energy and mass are equivalent, as expressed in Einstein's famous E equals mc2 E equals mc2. The kinetic energy of motion contributes to the object's inertia, making further acceleration harder. The mathematics reveal an asymptote. As velocity approaches light speed, the energy required to accelerate further approaches infinity. To push even a single proton to the speed of light would require more energy than exists in the visible universe. But there is an even deeper, more philosophical reason faster-than-light travel is forbidden: causality. In relativity, now is not universal. Two events that appear simultaneous to you may not be simultaneous to someone moving relative to you. This relativity of simultaneity has a startling implication. If you could send a signal faster than light, you could create scenarios where the effect precedes the cause. Imagine a spaceship traveling faster than light from Earth to a distant planet. From some reference frames, the ship would arrive before it left. You could, in principle, send a message to your own past. This isn't just theoretical. Mathematically, faster-than-light motion allows for closed time-like curves, paths through spacetime that loop back on themselves. These create paradoxes, like the famous grandfather paradox, where you could prevent your own birth. Physics cannot tolerate such contradictions. The laws of the universe must ensure a consistent, unidirectional flow of cause and effect. The speed of light, it turns out, is the cosmic speed limit of causality. It ensures that information, influence, and consequence cannot propagate faster than this universal constant. So, the light barrier is not merely a traffic law of the cosmos. It is the foundation of a coherent, logical universe. But what if we could obey the letter of the law while violating its spirit? What if, instead of moving through space faster than light, we could move space itself? This is where Einstein's later masterpiece, General Relativity, comes into play. Published in 1916, General Relativity reimagined gravity not as a force, but as curvature in the fabric of spacetime. Massive objects like stars and planets warp the geometry of the universe, and other objects move along the curves of this warped landscape. Crucially, general relativity distinguishes between motion through space and the behavior of space itself. While nothing can move through space faster than light, space can expand, contract, or warp at any speed. We see this in cosmology. During the Big Bang, space expanded faster than light. Today, galaxies beyond the cosmological horizon recede from us at superluminal speeds because the space between us is stretching. They are not moving through space faster than light. Space itself is carrying them apart. This distinction is not a trivial loophole. It is a fundamental feature of relativistic physics. And it opened the door to one of the most tantalizing ideas in theoretical physics, the warp drive. In 1994, Mexican physicist Miguel Alcubierre performed a remarkable calculation. He asked, could general relativity permit a space-time geometry that effectively moves faster than light without violating local light speed limits? His answer, now known as the Alcubierre metric, was a resounding yes. The concept is elegant. Imagine a bubble of flat space-time, like a calm region inside a turbulent wave. Ahead of the bubble, space-time contracts, pulling destinations closer. Behind it, space-time expands, pushing the starting point farther away. The bubble itself, and anything inside it, is carried along by this wave of geometry. Inside the bubble, you feel no acceleration. Your local speed is zero relative to your immediate surroundings. But to an outside observer, the bubble moves through the universe at speeds that could exceed light speed. It's like surfing on a wave. The surfer doesn't move through the water. The wave does, and the surfer is carried along. Similarly, a warp drive doesn't move through space. It moves with space. The Alcubierre metric was a mathematical revelation. It showed that general relativity does not forbid faster-than-light travel in principle. It merely forbids moving through space faster than light. By manipulating space-time itself, we might, in theory, travel to the stars in days instead of millennia. But then came the bill, and the universe presented an invoice stamped with impossible demands. To create the Alcubierre geometry, you need something called exotic matter, matter with negative energy density. Unlike normal matter, which warps spacetime to create attraction, exotic matter would warp spacetime to create repulsion. It would be the anti-gravity needed to compress space ahead and expand it behind. Does such matter exist? In theory, yes. Quantum mechanics allows for temporary, microscopic regions of negative energy through effects like the Casimir effect, where two parallel plates in a vacuum experience a tiny attractive force due to restricted quantum fluctuations. But the amount of negative energy required for an Alcubierre warp bubble is staggering. Early calculations suggested energy equivalent to the mass of Jupiter. Later refinements reduced it, but even the most optimistic estimates require negative energy far beyond anything achievable with known or even speculated technology. Worse still, quantum mechanics imposes energy conditions that seem to forbid large, sustained regions of negative energy. Negative energy can exist, but only in tiny amounts and for fleeting moments, balanced by larger amounts of positive energy nearby. The universe appears to allow negative energy only as a short-term loan, with immediate and steep repayment. So, the first layer of defense is energy. The warp drive requires a form of matter that may not exist in usable quantities. But the problems only deepen from here. Even if you could procure enough exotic matter, a warp bubble creates an event horizon, a boundary that causally disconnects the interior from the exterior. Once inside, you cannot send signals forward to steer or stop the bubble. Light from the interior cannot catch up to the bubble's leading edge if the bubble moves faster than light. You are, in essence, a prisoner in a superluminal train with no controls, no brakes, and no way to see what lies ahead until you arrive, if you arrive at all. Navigation becomes impossible. Collision avoidance is non-existent. Stopping requires an external mechanism, someone or something at your destination to collapse the bubble, a coordination challenge of absurd proportions for interstellar travel. Then there is the issue of quantum instability. At the boundary of the warp bubble, where spacetime curvature is extreme, quantum effects would generate intense radiation, similar to Hawking radiation at a black hole's event horizon. This radiation would flood the bubble's interior with lethal particles and potentially destabilize the geometry itself. Finally, causality rears its head once more. Even with a warp drive, traveling between 2 points faster than light can still create closed time-like curves if round trips are possible. Some physicists, like Stephen Hawking, have proposed a chronology protection conjecture, the idea that the laws of physics prevent time travel by destroying any configuration that would enable it, perhaps through quantum instabilities. So, the warp drive's problems are layered: energy, control, stability, and causality. Solve one, and another emerges. The universe guards its speed limit with a defense in depth. In recent years, researchers have attempted to design subliminal warp drives, configurations that work below light speed using only positive energy. These are mathematically possible, but they offer no clear path to superluminal travel. The transition from subliminal to superluminal is not smooth. It involves a fundamental change in geometry and causality. Other proposals have explored modified theories of gravity or nonlinear configurations of ordinary matter to generate warp-like effects. None have yet overcome the core issues. The pattern is revealing. Every theoretical advance in warp drive research uncovers new constraints. The universe does not say no with a single law. It says no with an interconnected web of physical principles: relativity, quantum mechanics, thermodynamics, causality. This suggests that faster-than-light travel is not merely an engineering challenge. It may be a fundamental impossibility, a feature, not a bug, of our universe. But what if impossibility is not an endpoint, but a beginning? What if the true value of the warp drive is not in taking us to the stars, but in teaching us about the universe? Humanity has always learned more from limits than from freedoms. The impossibility of perpetual motion taught us thermodynamics. The impossibility of absolute certainty taught us quantum mechanics. The impossibility of seeing the infinitely small taught us particle physics. The light speed limit is another such teacher. It reveals that space and time are not separate, but woven into a four-dimensional fabric. It shows that causality is not an abstract concept, but a structural feature of reality. It demonstrates that energy and geometry are intimately linked through Einstein's field equations. In seeking to break the light barrier, we have not found a shortcut to the stars. We have found a deeper understanding of the cosmos. We have discovered that the universe is lawful, consistent, and elegant in its constraints, that it permits life, consciousness, and curiosity within those bounds, that we are part of a cosmos that allows us to ask, what if, even when the answer is, you cannot. So, where does that leave our dream of interstellar travel? If faster-than-light travel is fundamentally impossible, then our path to the stars will be slower, longer, and more patient. Generation ships traveling for centuries. Seed ships carrying frozen embryos or digital minds. Robotic probes on thousand-year journeys. Maybe even uploading human consciousness into light-speed data streams. These are not science fiction. They are engineering challenges within known physics. They require no exotic matter, no warped space-time, only patience, perseverance, and a commitment to a future we may never see. But perhaps that is the point. The universe does not owe us shortcuts. It offers us a vast, beautiful, mysterious cosmos to explore within the rules it has set. And those rules have allowed galaxies to form, stars to shine, planets to orbit, and life to arise. We are the universe becoming aware of itself. And part of that awareness is recognizing our limits, not as disappointments, but as revelations. Tonight, look up at the stars again. They are distant. They will likely remain distant for generations to come. But their light still reaches us, crossing the void at the universe's ultimate speed. That light carries information, history, beauty. It reminds us that even within limits, connection is possible. Understanding is possible. Wonder is possible. The math may permit warp drives. The universe resists them. And in that resistance, we learn not just about space-time, but about ourselves, a species bold enough to imagine the impossible and wise enough to accept the possible. The stars may be forever beyond our quick reach, but they are not beyond our understanding. And perhaps, in the end, that is the greater journey.